Hi. So now we're moving on to actually starting to talk about Chapter 7, the formation of ions and ionic compounds. And we need to start talking about ions with valence electrons because the central driver for why atoms form compounds is in order to have a full outermost energy level. And we call that outermost energy level the valence electrons. And so how many electrons do these atoms have to begin with? So this is just another graphic. You've seen something very similar to this in the past. But here, and these are called Lewis dot or electron dot diagrams, where just really a dot is standing for an electron. So we know that beryllium has 2 valence electrons. So here are, just 2 dots representing those 2 electrons. And most importantly, we look over at our noble gases, and we see that our noble gases have neon has 8, argon has 8, helium only has 2, but what that represents is a full outermost energy level, and that's really important. That's what these atoms are trying to obtain. So just as a reminder, everything in that first column has 1 valence electron. Beryllium has 2, boron has 3, carbon has 4, nitrogen has 5, oxygen's group has 6, fluorine's group has 7, neon and everything below it has 8, but helium only has 2. And the elements in the middle all have 2 valence electrons. It becomes less important because, as we will see, they form ions a little differently than other elements. One of the things we talked about in the periodic tables chapter was that metals tend to lose electrons to become stable and nonmetals tend to gain, and we will see that on the next slide here. So again, these are the learning objectives of this, and I just wanted to reiterate here the octet rule that elements will gain or lose electrons until they have 8 in their valence energy level, with the exception of some of the smaller like lithium and beryllium, because if they lose electrons, they only have electrons in the first energy level. So now let's take a look at the formation of anions and cations. So anions are the negative ions. We learned that last chapter. Cations are the positive ions. Nitrogen. So the first thing we're going to do is we're going to take a look at nitrogen. And I'm going to use 2 different colors here so that we can maybe better understand what's going on. So nitrogen's orbital diagram is 1s2, 2s2, 2p, 3. And in order to get that outermost energy level, so that would be the valence, so that would be these 2 sublevels, in order to get them full, what nitrogen is going to need to do is gain 3 electrons. So I'm just going to write those in a different color, just so that we understand that its normal valence electrons, it ends in 2p3, it adds 3 electrons. Now it ends in 2p6, so that's nice and stable. If we do the same thing with sodium, sodium is 1s2, 2s2, 2p6, and 3s1. And now if you look at this, what would happen? Well, if it was going to try and get a full 3rd energy level, it would need to gain 7. So what happens is this electron goes away. And now if we look at the electron configuration that's left over, these guys actually would have the same electron configuration. They would have the same electron configuration as the element neon. Neon is, of course, a noble gas. If 2 elements have the same electron configuration, we call them isoelectric, by the way. This just shows us maybe in a little bit more graphic form of what's going on. So the anions, negative ions, they tend to gain electrons, or they have gained electrons. So remember, nitrogen 1, 2, 3, 4, 5. Those are nitrogen's original electrons, and it has gained 3 in order to have a full outermost energy level, which is why it's 3 minus. Oxygen has 1, 2, 3, 4, 5, 6 typically, and it gains 2, so its charge is now 2 minus. Right? Fluorine normally has 7. 1, 2, 3, 4, 5, 6, 7. Of course, it gains 1, and that's how it has a charge of negative. Now, if you look at the elements below, you see that there's no dots around them. Well, that's because their outermost energy level only had a few electrons and they have been erased. So sodium, if you look at the previous couple screens, sodium of course has 1 valence electron. Calcium has 2 valence electrons, and aluminum has 3 valence electrons. But what happens when it forms an ion is that it loses those electrons. And so that its inner core electrons now become their valence. So to draw the electron dot diagram of ions, draw the correct number of electrons in brackets and then the charge of the ion. If it's going to have a charge, we put brackets around it. Right? Negative ions will tend to show their electron configuration of the next noble gas to include the extra electrons the negative ion gained. That's what we're seeing up here. And so positive ions will show an empty electron shell after the valence electrons have been removed, and that's what we're seeing down there. Now, transition metals get a little bit trickier, and this is why, because they can form more than one different ion. I'm just going to flip back up here. If you think of nitrogen, nitrogen has 5 valence electrons. How can it become stable? It's got to gain 3. And that is a rule, and it will never form any other ion than 3 minus. But transition metals, one of the properties of them is that they can often form more than one different ion. So we're going to write here the electron configuration of iron. So we're going to do Fe. So we'll just do the noble gas configuration. So the noble gas is argon, and then it's 4s2 3d6. If it loses 2 electrons, this is key, it actually will wind up losing its 4s electrons first. So if it loses 2 electrons, it would be same argon, but then just 3d6. That is sometimes difficult for students to understand. Why doesn't it lose why doesn't it lose the last ones filled? It loses the ones that are on the outside. When it loses 3 electrons, this is when it moves to 3d5, because it loses its 2s, and then it starts losing its d electrons. We'll see why this might be advantageous in a moment. So if I do its orbital diagram, this may get a little small here. So here's argon, and then it would be, 4s2, and then 1, 2, 3, 4, 5, 3d, and 1, 2, 3, 4, 5, 6. Now think about its ion after it loses 2 electrons. Remember, it loses the s electrons first. So it would still have this argon core, but now no 4s. 4s is completely gone. If you want me, I can leave it blank. It would just be this 1, 2, 3, 4, 5, just be 3d6. And that is stable. With those 2 valence electrons, the outermost electrons gone, it is stable, even though the d orbital is not full. But under some circumstances, iron can also form a 3d5 ion, so losing 3 electrons. So 1, 2, 3, 4, 5. And this is also stable because it has a half-filled sublevel. Remember, electrons are negative like charges repel. So these two electrons right here being in the same orbital, if that wasn't the case, the atom would still be stable, would actually maybe be more stable. So iron can lose 2+ or 3+. That happens with many of the transition metals. So of course the symbol for a neutral iron is iron. The symbol for iron losing 2 electrons would be iron 2+. And the symbol for losing 3 electrons would just be iron 3+. And this diagram right here shows all of the common ions for most of the elements. And so you can see over on the right-hand side that we have all of our nonmetals here, and our nonmetals making negative ions, right? Negative ions means that they've gained electrons. And then over on the opposite side of the periodic table, we see all our metals making positive ions, and everything in this first column making a +1, everything in the second column making a +2. You notice that in the middle there, we get those transition metals, and you will see that, these are just some, not all of the ions forms, these are just some. And the dominant one is on top, and for most of the transition metals, the 2+ is the most common, and then there might be another one that will also occur. So as a general rule, we can try and remember that since everything in group 1 has one valence electron, it forms a positive ion. Just +1, and we don't write it. Everything in the second group, the alkaline earth metals, forms a 2+ ion. And yes, we do write number and then the charge. In the transition metals, can't really say. Then we go to this group right here, group 13, aluminum's group. Generally, they form 3+ ions, but remember, boron is a metalloid, so it doesn't form ions the same way that metals form ions. In carbon's group, I tend to just say, well, skip it, because carbon and silicon don't really form ions, and then you're left with metals, and those metals often form 4+ ions. We will address that. How do I tell which one it is? We address that in a moment. Then we get to nitrogen's group, which forms 3- ions. Because they have 5, they need to gain 3. Oxygen's group is 2-, fluorine's group is 1-, and then of course the noble gases don't gain or lose electrons. So we think of the pattern. It's like 1, 2, 3, skip, 3, 2, 1, skip. If you remember that pattern, then you can tell the ions that will be made from the representative elements. And then the transition metals, we just need to know that they can make various ions, and we will learn how to tell which one it is in a little later on video.